All right, welcome back. So, what we're going to do today, continuing from our last section, is talk about some rules of inference. So, what are rules of inference? Well, if you recall in the last section, we've talked about the rules of logic, which mostly include ands and ors. Now, are those the only rules that are out there? And obviously, you can guess that no, there are probably rules that are involving things like implication as well as biconditionals, and those we really haven't really discussed in our class in the last section. So what we have done so far is basically give an introduction on all of the connectives. So we have the negation connective, we have the and, we have the or, we have the two types of ors. We have the implication and we have the biconditional. So what we're going to continue on today with are the biconditionals and the implications. Now, just as a review, what we've done so far is be able to use some of the laws for ands and ors, and these are called laws of logic, and we talked about them here. And these are essentially patterns that we can say one form, one expression is logically equal to another. So saying one is logically equal to saying another. Now, notice the equal sign here, the logical equal sign here. We have an equal sign, and then we have basically a two-way arrow. I want you to keep this in mind as we continue our discussion today. So meaning that these rules can go both directions. Okay, so for example, if I have a y or x, I can go back and say this is equal, this is logically equivalent to x or y, and the other way goes as well. So if I have x or y, I can say that I have y or x. So there's a bi direction here that goes in both directions. Now, the laws that we're going to talk about today are slightly different, so please keep that in mind. So that's one thing we talked about. Another thing that we discussed last time was drawing these truth tables. So, according to the definitions of these connectives that we have, each connective has its associating definition, and we went through that in the last section. So here, we can draw, if we wanted to ever figure out whether two expressions are equal to each other, we can draw a table and see if they match. If they match, then that means they're logically equal. If they differ in even one of the rows, then they are not logically equal. So again, keep that in mind, and the situations where we use the table and where we use algebra would be slightly different. And I do invite you to review the videos for that. All right, so given implication, so we're going to start with our rules of inference now. Given an implication, P implies Q, there are other implications that can be defined as well. So let's give a very simple example here. Again, this is very similar to the example that I gave last time. So let's say I have a P, and the statement P is today is Sunday. Okay, so today is Sunday. And Q is the statement today I go to church. Okay, now if I told you that for me, P implies Q. Now I'm just gonna write out our table here just in case we forgot. So our table goes something like this: 0, 0, 0, 1, 1, 0, 1, 1. So our four cases, and we said an implication is only false. The only case that it's false is when P is equal to 1 and Q is equal to 0. So here we have a false, but then every other case it's true. Now, if we read out the implication, the sentence that is being described here, it says, today is Sunday, implies that today I go to church. Or another way to say that is, if today is Sunday, then today I go to church. Now, understand that this is a rule. It's kind of like a law for about myself. So I'm claiming that if today is Sunday, then you're going to see me at church. Okay, so you can reason why there's only one false case. The only way that that statement would be made false, could be claimed to be false, is if P is equal to 1. So if today is Sunday, but I did not attend church today. So if Q was false, then that would be a false statement. Okay, so I think I hope that makes sense to everyone. Now, let's try to reason. Let's try to add a few more definitions to this implication. There is one called a converse. Okay, so the converse goes like this. So we have a statement Q implies P. Okay, so right now, what I want to figure out is, do they have the same logic? Okay, so is it true that P implies Q is logically the same as Q implies P? Now, if we read the sentence, it is saying that today I go to church implies that today is Sunday. So another way to say that is, if today I go to church, then today is Sunday. Now, at this point, I want you to realize that if this is hard to understand, then please pause the video and just convince yourself that in fact these two are not logically equal to each other. Okay, so P implies Q is not logically equal to Q implies P, because Q implies P says if today is if today I go to church, then today is Sunday. So it's basically making a guarantee to be a Sunday. Well, that might not be true, because what if I go to church every day, right? So when I say today is Sunday implies that today I go to church, I'm making a point about Sunday. The only thing that you know is about Sunday, right? That I go to church. But can I say the opposite? Can I say, if today I go to church, then today is guaranteed to be Sunday? And the answer is no, I can't, because I could go to church every day. I could be a pastor, right? I could go there every single day. So I hope you can see that the logic here is not the same. And in fact, if we draw a table for Q implies P, it looks like this. So, what if we claim that they are equal? So, what we're really claiming here is that we are actually making a wrong deduction, and this is called confirming the conclusion. Sorry, I'm running out of room here, but it's called confirming the conclusion. So, confirming the conclusion means that because I know that P implies Q, I can then say Q implies P. That is wrong. That is confirming the conclusion. So that is a false application of logic. So it's often called what we call a fallacy. So this is called a fallacy. So it's a fallacy of confirming the conclusion. Okay, what's next? Well, what about the inverse? The inverse is not P implies not Q. Okay, so again, let's say you're told that if today is Sunday, then today I go to church. Okay, can I then say, is it logically equal to say that if today is not Sunday, then today I don't go to church? Okay, so if today is not Sunday, then today I don't go to church. So is that logically equal to say? And again, I hope you can see, again, if you need some time, you can pause the video here, that it is actually not the same as saying the original implication. Because once again, I can go to church every day, right? So I can go to church every day. Just because today is not Sunday, it does not guarantee that today I don't go to church, right? It could be a Monday and I'm at church. Okay, and that's okay under the first expression here. So again, I want to claim that those two are not logically equal as well. And again, you'll see, you can verify this in a table. So just verify my work here. You'll see that the table is actually very similar to the one that we had before. And this fallacy is called denying the hypothesis. Okay, so just remember, these are just terms that people use in arguments to say that no, you're wrong because here you are confirming the conclusion, or no, you're wrong because you are denying the hypothesis. Okay, so these are just terms that are used in arguments. All right, last example here, we also have the contrapositive. The contrapositive is defined as not Q implies not P. So is not Q implies not P the same as the original expression? So again, if what you know is if today is Sunday, then today I go to church. Is it the same logic to say if today I don't go to church, then today is not Sunday? Again, take a second to think about that. Okay, I'll give you the answer right now is that it is true. It is logically equal. So if today I'm not at church, the only thing you can say, the only thing you can guarantee is that it's not Sunday. Okay, so I'll just kind of put it down here, and that we can say P implies Q is logically equal to not Q implies not P. In fact, this is a rule that I want to add to the list of laws that I already know. So if you remember the laws of logic that we had from last time, I want to add this law. This is the law of contrapositive or contraposition. You'll hear some people say. So the contrapositive law says if P implies Q, then not Q. So the negation of the conclusion implies the negation of the premise. So not Q implies not P. So this is a contrapositive law. So let me just highlight that, or you can even add it to the list of the laws that we already took a look at before. All right. So what else can we say about implications? Well, one other thing is that before we looked at a law called De Morgan's law, and again, if you're not familiar with De Morgan's law, please have a look back at the laws of logic. But De Morgan's law basically says that if I have a negation and I put it inside of a bracket, if we had an or inside of the bracket, those ors will now have to become ands and vice versa. So here, I want to figure out what it is that negation of P. So here I'm doing example 222. I want to figure out what the negation of P implies Q is. So again, going back to our previous example, if I said today is Sunday, implies that today I go to church. But what if you say, no, that's not true. It is not the case that if today is Sunday, then today I go to church. It's not the case. So, what exactly are you saying? Well, let's apply a little bit of law. Now, look back in the laws of logic. We'll find that P implies Q is equivalent to not P or Q. And in fact, we drew a table for both sides to indicate that they are equal, but this is called the implication reduction law. Okay, so this is the implication reduction law that says P implies Q is equal to not P or Q. And now I'm going to distribute this inside. So we have not P or not Q, and that was using De Morgan's law. And now we have a double negation law that says when we have not, those two nots disappear. So we have P. Sorry, I actually have an and here. So remember De Morgan's law, when we distribute the negation inside, this or has to become an and. So my apologies there. So now we have P and not Q from double negation. Okay, now how do we read this? Well, if you want to say that no, it's not true that if today is Sunday, then today you go to church, then really what you're saying is today is Sunday and today you didn't go to church. Right, so that is the outcome of this statement. Now if you think about it, yeah, in fact that does make sense, because if I claim that every Sunday I'm at church and you say no, today is Sunday and you're not at church, then that is a false statement right away. Okay, so try to keep this in mind, because rules, implications, like laws that we claim, can be falsified by claiming a case that P is true while Q is false. Okay, so uh, we we can negate that statement. Okay, so it does say in the notes here that it says, unlike conjunctions and disjunctions, the negation of an implication does not exhibit a dual behavior. So don't read too much into this statement. All I'm saying is that when you distribute the negation inside of an implication, it doesn't act like flipping the ands and ors, right? So it's not as easy as flipping the ands and ors. In fact, I'm showing you in this example that when we negate an implication, we are actually having an and. It's actually equivalent to an and statement. All right. So the last thing I want to say here is that the laws that we talked about in the last class, we said all of those laws are what we call logically equivalent. Okay, so when we say P is logically equivalent to Q, we have an equal sign and a double arrow. Okay, so really what that means is that the biconditional is a tautology. So we talked about that in the last class. And now the laws that I'm about to present to you are called logically implies. So when I say P logically implies, I'm going to use this symbol. And this symbol is kind of a forward direction. And it says, when P is true, then Q must be guaranteed. Okay, so these are laws that when P is true, Q must be guaranteed. And this is the case when P implies Q is a tautology. Okay, so all of the laws that I'm about to talk about right now are logically implies laws, and this is a whole new set of laws that we're going to use in this class. All right, so the rules of inference are found in your textbook. So I will refer you to the textbook to read a little bit more about this, but I'm going to introduce you to a few of the rules, and these rules we're going to use throughout the class today, and we're going to use them in logical inference. So, what logical inference means is that I don't only want to show that two expressions are equal, but from a set of expressions, from a set of logical expressions, I want to come up with new expressions. So, new laws that are also true based on the things that I know. All right, now this might sound foreign for now if you've never heard of this before, but stick with me. So we're going to start from the basics. The first thing we're going to do is introduce all of the laws that we have here. So the first one I want to look at is called modus ponens. Now, notice that we have an implication here. We have this implies. Now, all of the rules that you're looking at here, from modus ponens all the way down to a rule of disjunctive amplification, all of them include an implication. Okay, so all of them have an implies. So, what this is saying is we have this implies. In fact, I should put a double arrow here because all of these happen to be tautologies. Okay, so if you have a second or if you want some extra practice, take a look at all of these laws and prove that each of these laws are actually tautologies, are all true. Okay, so always true. So P and P implies Q always implies Q. Okay, what does that mean? Well, we usually write an argument in the following form. We always write it like this. So I'm going to write modus ponens here. So modus ponens says I have P and I have P implies Q. Okay, so I have P and I have P implies Q. This allows me to be able to conclude Q. Now, this final implication here, so again, as I said, there's always one main implication. So that final implication is talking about a conclusion. So you can imagine that whenever I draw a line here in the argument, I'm really talking about an arrow that is pointing down. Okay, so it's an arrow that's pointing down. Okay, so how can we read this argument form? Everything above the line are called premises. They are assumed to be true. Okay, once again, everything above the line are premises and they are assumed to be true. And this is the argument form that we're talking about. Okay, so everything below the line is called a conclusion. Okay, and they are things that we can conclude, things that we can gather from the information that's above the line. So if I tell you that, well, let's go back to the previous example. Let's say that you know if I'm taller than 6 feet, then I'm taller than 5 feet. Okay, so this is that statement. If I'm taller than 6 feet, then I'm taller than 5 feet. And you know I am taller than 6 feet, then what can you conclude from this? Well, you can conclude that I am taller than 5 feet. Okay, so once again, if you know that I'm taller than 6 feet, and if you're taller than 6 feet, then you're taller than 5 feet, then you can conclude that I'm taller than 5 feet. Okay, so this is a statement that is always true. Another example would be if you know that if today is Sunday, then today I go to church, and you know it's Sunday, then you can guarantee, you can conclude that today I'm at church. Okay, so once again, if everything above the line is is assumed to be false, sorry, let me let me say that again. If everything above the line is assumed to be true, then everything below the line is concluded to be true. as well. Okay, so that's what an argument form is. So that is called modus ponens. Okay, there's another one called modus tollens. So modus tollens is this one, this third one right here. So what modus tollens says is if I have P implies Q and I have not Q. Now notice that I know the order looks a little bit different here, but the order doesn't actually matter because everything above the line is assumed to be true, right? So modus tollens, if you know P implies Q and you know Q is not true, then you can conclude that P is not true as well. Okay, so another example. If I'm taller than 6 feet, then I'm taller than 5 feet. You know that's true. You also know that I'm not taller than 5 feet. So if I'm not taller than 5 feet, the thing that you can guarantee from that is that I am not taller than 6 feet. So that is called modus tollens. And you know that this is a guarantee. So just convince yourself that logically this will work all the time. Everything above the line being true guarantees everything below the line. Okay, next one. We also have one called syllogism. Syllogism says, now syllogism is a little bit more complex here, but syllogism says P implies Q and Q implies R, allows us to conclude that P implies R. Okay, if I'm taller than 6 feet, then I'm taller than 5 feet. If I'm taller than 5 feet, then I'm taller than 4 feet. So therefore, in conclusion, if I'm taller than 6 feet, then I must be taller than 4 feet. Okay, so what syllogism is saying is if we have an implies and there's this Q in the middle, we can skip the Q, okay, because there's an implication that is going this way. So P implies R automatically. So we have that syllogism. Next, we have let's look at disjunctive syllogism. Okay, so disjunctive syllogism is this one right here. So if I know P or Q, if I know not P, then I know Q. Okay, so it's either P or Q. Okay, so the first statement is saying it's either P or Q, and it's not P. Right, so it's either P or Q. It's not P. So which one is it? It has to be Q. Right, so P or Q, not P, therefore Q. Again, everything above the line being true guarantees everything below the line. All right. What's another one here? We have a conjunctive simplification as well. So conjunctive simplification says P and Q. Okay, so if I have the statement P and Q, I can break them up into two parts. I can break them up into P and I guess realistically, I can break it up into Q as well. So essentially, what conjunctive simplification says is anytime I see an and, I can break them up into two separate statements because they both have to be true. So again, if I said today is Thursday and today is sunny, then surely each one of those statements have to be true, right? So we might be able to look back at, for example, the modus ponens law. So you see here, modus ponens, we have P and P implies Q. So you see we have this and here. So therefore, we can just break it up into those corresponding parts. Okay, so I hope you can see what I'm getting at here. Okay, finally, I want to talk about one last one, which is the disjunctive amplification. Actually, there is actually one more law I want to point your attention to, but here's the disjunctive amplification law, which says if I know P is true, okay, P is already true, then P or Q is true. And what is P? What is Q? Q is anything here. Okay, so Q, it doesn't matter if it's true or if it's false. It will be an automatically a true statement. So for example, if I say 1 plus 1 is 2, or, and that doesn't matter, right? So I can say anything after that, that will be a true statement. So 1 plus 1 equals 2, or aliens exist. That's a true statement. Okay. So again, understand that these argument forms are ones where everything above the line being true is going to guarantee everything below the line. Okay, there's one last one here, which is if I have P and I have Q, so if those two things are true, I can say P and Q. I can combine them to make it P and Q a statement. So this is the rule of conjunction. Okay, so notice that we have a rule of conjunction and we have a rule of conjunctive simplification. So they're really backwards, right? Those two laws are really backwards laws of each other. Or another way you can say that is that we P and Q, like writing it like this and writing it like this part and writing it like this, they're exactly the same. Okay, so just keep that in mind. Now, what are we going to use these laws for? Well, it turns out that these laws are actually pretty important for making certain types of proofs. So in a second, I'm going to show you a bunch of proofs, but in your textbook, you can also read about conditional proof, proof by cases, constructive dilemma, and destructive dilemma as well. So I invite you to read up on those. I'm going to show you how to prove some of those, but in your own time, take a look at what those proofs are representing. They are just forms that are always going to be true. By the way, one last thing about argument forms. All of these argument forms, all of these arguments that we just wrote up here, these are what we call valid arguments. Okay, so what valid arguments means is if everything above the line is true, that will guarantee everything below the line. Okay, so there are ways that we can prove validity, validness for a particular argument. Okay, so let's look at some of those arguments, some of the arguments that we can show to be valid and even invalid. So here's the first example. So let's say I give you an argument that looks like this. We have P and Q, and then we also have P implies Q implies R, and therefore R. Now, this might be an argument that you've translated from English, and we'll talk about how to do that in 1 second. But let's say somebody said this to you, and you want to figure out, oh, is this a valid argument? Are they saying something that's true, or is it that's an invalid argument? So, once again, what a valid argument is that if everything above the line is true, if all the premises are true, this is going to guarantee the conclusion. So typically, if we want to prove an argument to be true or valid, we want to show an argument to be valid, then we need to assume the first two things. I'm going to put the number one and number two here just to indicate that these are premises and they are meant to be true. So the first thing we'll do is we'll label these as premises. A premise, once again, is something that we assume to be true. So now that we know that number one and number two are true, can we derive other things from the laws that we know? Can we derive other things that we know to be true? And here, I think we can. But before we go on, I want to point out that these are forms that we can use, right? These are argument forms that we can use. But we can also use the laws that we know from last class. So the laws of logic, like De Morgan's law, like associative law, distributive law, all of these laws are still valid here. We can still use these laws in order to show the conclusion. So once again, the question that's being asked here is if number one and number two are true, can the conclusion be concluded? Is the conclusion also true as well? All right, so let's try to prove this. So number three. Okay, so I'm just going to start writing things down to be true. So I'm going to use this arrow to begin with. So if number one and number two are true, this logically implies number three. Now, can you see any of the laws that we've talked about that will allow us to be able to write a third thing that is also true? So again, if you want to test yourself, you can just stop the video here and just take a look at the laws and see if there's anything that you can come up with. So what I see is I see this conjunctive simplification. Okay, this conjunctive simplification law says if I know P and Q is true, then I can individually write P and I can also individually write Q. So this is from the conjunctive simplification of number one. This is from the conjunctive simplification of number one as well. Okay, now remember I said in the laws of logic, in an exam, I typically won't ask you to write down the laws, like which laws you use, because in the laws of logic, usually it's pretty clear. In the rules of inference, I will remind you to write down the laws that you've used, because there's actually, once we get to larger and larger expressions, there's just many ways that we can that we can prove certain things. So right now we have P, we have Q, and now we know four things to be true. Okay, what else? Well, if we take a look a little bit closer here, we have a P that's true, and then we have a P implies. Now, remember last time what we said, whenever we have a bracket, this bracket can always be substituted for something. So let's substitute this bracket to be X. Okay, so let's say this bracket, everything that's inside that bracket is X. So we have P and we have P implies X. Okay, so what do we have? Well, modus ponens says that if we have P and we have P implies X, then we know X. Okay, so number 5, I can say that I have Q implies R. So that is the X, right? I'm just going to take away this bracket, because now this is what we know from modus ponens of number 3 and number 2. Okay, so from number 2 and number 3, this is what I can gather, number 5. And again, please be sure when you do these when you do these proofs, that you write down each step, right? Because you have to be clear how you got the next step. Okay, number 6, how can I reason from the rest that I have? Well, I have number 4, which says Q is true, and then I have 5, which says Q implies R is true. So now I have Q implies R, I have Q, therefore I must have R. And this is going to be modus ponens of number 4 and number 5. Okay, so what did we see here? Well, we're at the conclusion, and what we found was that if I assume number 1 and number 2 to be true, then it implies number 3, which implies number 4 and implies number 5 and also implies number 6. So therefore, ultimately, we've shown that number 1 and number 2 implies number 6. And therefore, we're done. We can say that this is a valid argument. Okay. And this is always how we're going to show validity for an expression. So if ever we want to see, we're given a question, show the validity of this expression or show the validity of this argument, or that's what we intend to do, then this is what we have to do. We have to follow these steps. Okay. All right, let's do another one just so that we're happy with everything. Now, this one is going to be a little bit more tricky, because if you remember what I said last time, or in the previous example, we can also go back and use some of the laws that we know from before, the laws of logic that we know from before. So since we have these argument forms, I can now add those logic laws to it as well. So let's do the same thing. So here I want to show that this argument is valid. Okay, so here's number 1, number 2, number 3. Okay, so I have those 3. And I'm going to try to show that those 3 being true is going to imply Q or S. It's going to imply the conclusion. All right, so so how are we going to do this? Well, there's actually a couple ways to do this. And I'm going to go back and remind you of some of the laws that we've used before. So these, number 1, 2, and 3, are premises. Okay, so they are assumed to be true. All right, what else can we say from those 3? Well, if we take an aside a little bit, if I take a look at this P or R, okay, now I'm just going to write down the answer here, but P or R is actually the same as saying not P implies R. This is an implication reduction. Right? Now, just take a second just to convince yourself. I'm actually going to write it on the side here in black. So we have not P or R, or sorry, not P implies R. So we have not P or R. So just understand that this part, right? So if I put a bracket there, the bracket goes like this, right? So I have not P or, oops, sorry, not P or R. And then now I have a double negation, which just gives me P or R. So I hope you can see that number 3 is equivalent to number 4. So if they are logically equivalent, then surely it implies, right? So notice that implies is actually a weaker version of logically equals. Okay, so it's a weaker version of logically equals. All right, so now what can we do? Well, I think now we can do a little bit more because now everything is implies. So I have number 4, which is P, not P implies R, and I also have an R implies S. Now, do you remember earlier we talked about this syllogism law, right? That if there is a middle implication, that middle variable can just disappear. So this also implies number 5, and number 5 is not P implies S. So you see, not P implies R implies S, not P implies S. So I can skip the R. And this was called the syllogism. Oops. Syllogism of number 4 and number 2. And this is just looking for patterns, right? So whenever we do these proofs, that is all we need to do. We just look for patterns and then we come up with the final solution. Okay, what else? Well, in this case, we're a little bit stuck. So again, take a look. You can pause the video and take a look at see if there's any other laws that you can apply. We're a little bit stuck here, but we did talk about a law earlier today, which is whenever we have P implies Q, we can also say not Q implies not P, and that was called a contrapositive law. Okay, so whenever we have P implies Q, I can say Q, not Q implies not P. So in this case, from the contrapositive law, I can say not S implies not P, which is just equal to P. Okay, so now I can say not S implies P, and that was called the contrapositive law of number 5. Okay, so now we have number 6. So not S implies P. We have P implies Q for number 1. So not S implies Q. So that is, again, the syllogism of number 1 and number 7. Sorry, number 6. So syllogism of number 1 and number 6. And then now, finally, I can say S or Q from the implication reduction of number 7. You see, same argument as what we had here, right? So if I have not S implies Q, I can say not S or Q, which will give me S or Q. Okay, so once again, we have a proof. This is a slightly longer proof. And in fact, there are other ways to do this proof. So I do invite you to see if you can find another direction to go to get this proof. In fact, this is just building on top of what we already know from last time. Okay, so you can just as easily use the laws of logic that we've discussed in the last class, in addition to using these argument forms. Okay, so let's do one more example here, just so that we can we have a better idea of proving and disproving. Now, here is an example. If somebody says this to you, if you send me an email, then I'll go out with you. If you don't, then I'll sleep early. In this case, I will wake up refreshed. Therefore, now there's the key term. Whenever you see therefore or in conclusion, you know that we are talking about a line for our argument form. So therefore, if I don't go out with you, then I'll wake up refreshed. Is this a valid argument? Is what they're saying a valid expression? So once again, valid means everything above the line being true guarantees everything below the line. So what we're going to do here is we're going to translate. We're going to translate to see if this actually is a valid argument. So the first thing we'll do is we're going to pick out all of the primitive statements. Now, if you don't remember primitive statements, go back and review. But primitive statement says that they are statements that are in the simplest form. So they don't have any connectives like and, or, if, then, biconditional. They don't have any of those. So here is one. If you send me an email, so let's call this S. Okay, so you send me an email, then I'll go out with you. Okay, we'll call this R. Okay, if you don't, then I'll sleep early. So sleep early is, we'll call this P. And then in this case, I'll wake up refreshed. wake up refreshed. Um, we'll call it Q. Okay. So here we're going to translate all of our sentences. So if you send me an email, I'll go out with you. So the first statement they're making is S implies R. So if you send me an email, then I'll go out with you. If you don't, then I'll sleep. Then I'll sleep early. So if you don't what? So I think here it is saying if I don't send you an email, then if you don't send me an email, then I'll sleep early. So I think it's not S implies P, right? So you kind of have to get the meaning of the sentence in order to do a good translation. Now, in this case, in what case? Well, in the case that I sleep early, I will wake up refreshed. That makes a lot of sense. So in the case that I sleep early, I will wake up refreshed. And therefore, if I don't go out with you, so what is if I don't go out with you? So not R implies that I will wake up refreshed. Q. Okay, so that's our first job, to translate everything into proper English, into its symbolic form. And now I want to figure out, is it a valid argument? So is it true that if I assume number one, number two, and number three, that I will eventually get to the conclusion to be true as well? So let's do that. So the first thing I see is number two and number three is a syllogism. So number four, I'm going to write down not S implies Q, because not S implies P and P implies Q. So that is syllogism of number two and number three. That is derived to be true. Another thing that I see here is that if I do a not S implies R, I can write not R implies not S, and that was from the contrapositive of number one. Okay, so again, recall that law. And number six, not R implies not S implies Q, so not R implies Q. And therefore, we have the conclusion. This is the syllogism of number four and number five. And therefore, we have the conclusion, and we can again claim that this is a valid statement. Okay, so that's great. So we have we have all of the tools. So I know we can do many more, and we're going to do a few more examples in the in class this week, and I'll go over them as well. But practice. So the only thing that we can do with these is practice the ones that are in the textbook, the ones that are in the in-class. Take a look at these examples again, just to make sure that you understand how to apply those laws. Essentially, what we're doing is taking a look at patterns that are above the line, right? So when we have the patterns that are above the line, we can then say that everything below the line is also true. So try to practice using these patterns. Try to use the patterns that we've talked about last week with the laws of logic as well. And this will help us in doing these types of proofs. Now, there's one last thing that I want to look at here. So before we look at that last thing, how do we know that these statements are actually true? So, for example, sorry, I should probably use a blank screen here. So let me go to a blank. Okay, so how do we know exactly that P implies Q, P therefore Q? Now this is modus ponens, so look back at the laws, and this is actually called modus ponens. So how do we know that this is valid, right? How do we know this? So another way to say this is that this can never be invalid, right? So it's valid because it can never be invalid. So what does it mean to be invalid? Well, again, let's review. What does this arrow actually mean? The arrow means guarantees, right? So everything above the line is true, guarantees everything below the line. So can we show this to be a guarantee? Well, let's look at it in the reversed way. Can it be that everything above the line is true while this is false? Okay. Can it be that if there's somebody taller than 6 feet, that they're also not taller than 5 feet? Can that happen? Okay. If we can say, no, that can never happen, then this must be a true law. This must be a valid law. Okay, so I'll say that one more time. Can it be true that P doesn't imply Q? Can it be that P doesn't imply Q? If it can, then it must be invalid. But if it cannot, then it must be valid. So how can I show that this is valid statement? Well, let's try to assign some values to P and Q so that the top of the expression is true, but the bottom of the expression is false. Okay, so essentially, if I tell you, if today is Sunday, then today I go to church, then can you find a Sunday that I don't go to church? Right? Because if you can, then that statement is invalid. Okay, so let's see if we can do that. Well, the first thing is, how do we make this true? How do we make this expression true? Well, I need to assign P to be true. So notice that if I assign P to be equal to 1, this is a true statement, right? That statement right there is true. Now, if I take a look at this statement, how do I make this statement true? Well, I need to assign Q to be 1 as well, right? So P implies Q. How do I make it true? Because P is already 1, Q must be a 1. It cannot be a 0, right? Okay, now the last thing is, let's take a look at the bottom. If I say, well, I want to make that statement false, then I must make Q equal to 0. Okay, so that's the first thing I do. I assign all of the variables so that they satisfy what I want. So the top has to be true, the bottom has to be false. Now, if I'm able to find a case like this, then I can say that this law is invalid, right? Because the top does not guarantee the bottom. However, what's the problem here? The problem is that we have a contradiction of Q's. The Q needs to be a 1 and a 0 at the same time, which can't happen. So what we can say here is that we tried, so we tried to find invalid case. Can we find an invalid case? No, we cannot. We cannot. So try to find an invalid case, we cannot. Therefore, it's valid. Okay. Now, is this a good way to find validity? So if I say show this thing to be valid, right? Is this a good way to show validity? The answer is yes. However, in an exam, I will typically say, if it's valid, if you find something to be valid, I also want you to prove it using the laws. So it's not enough to say, yes, this is valid, but you also need to prove it to me using the laws. Okay, so that would be in an exam. All right, so let's do a bigger example of this. What if I give you this expression and I said, is this valid? Yes or no? Is this valid or invalid? The first thing we need to do, okay, if we don't know, because right now I don't know if this is a valid or invalid statement. Maybe we translate it from English and we want to find out whether this is valid or invalid. The first thing we should do is try to assign true and false. Okay, try to assign everything above the line to be true, everything below the line to be false. Because once again, if we can find such a case right away, we can say this is invalid. Okay, we have a counterexample and this is invalid. Okay, so let's try to do that. So let's start with the bottom. How do I make the bottom statement to be false? Well, if you take a look at our table, the implies says that if I have a 1 here and a 0 here, okay, then this is false. So that would mean that S must be a 0 and T must be a 1. Okay, now again, take a second just to convince yourself of that, because for the implies to be false, the thing before the arrow has to be true. The thing after the arrow has to be false. Okay, so we have S equals 0, T equals 1. Okay, that will make the bottom case false. Okay, so I'm going to put check mark there. Good. Now let's go all the way up to the top. So now I have to make all of these 4 statements up here true. So let's start with P. That's the easy one. How do I make P true? Well, I need to assign P to be equal to 1. All right. So let's look at the second case. The second one says not P or Q. So if P is equal to 1, then this is equal to 0. Now again, take a look at your chart again. Take a look at the table for implies. 0 implies anything is true. So the fact that I've assigned P to be equal to 1, this statement is automatically true. It doesn't matter what Q is. Okay, so just take a look at the table again just to convince yourself, but 0 implies anything is true. Okay, what else? Let's jump to the bottom one here. The bottom one says T implies R. Well, T is already equal to 1. So what does R have to be? Well, here R has to be equal to 1. It cannot be 0. If R is 0, then that would make T implies R false. And we don't want that. Right? We want it to be true. So R must be 1. So if I know something must be this, then I'm going to write it down right away. All right, so the last thing I need here is R is equal to 1 and S is equal to 0. So 1 implies 0 is 0. So imagine that this bracket is going to give me a 0. The bracket gives me a 0 currently. So what implies 0 is true. Okay, what does Q have to be? And the only thing Q can be here is a 0. Q cannot be a 1 because 1 implies 0 is false. Okay, all right. Now, notice the difference between this example and the one that we just did with modus ponens. The difference with this example is that there's no contradiction. So if I assign Q to be 0, P to be 1, S to be 0, T and R to be 1, this will give me a case where everything above the line is true, but everything below the line is false. So this is called a counterexample. And the counterexample, because we have at least one counterexample, we can now claim this argument is invalid. Okay, so now we can claim that this argument is invalid. Now, let me just very quickly review what I just said. We have a counterexample, right? Therefore, I can find one case that is not true, right? This implication is not true in at least one case. Okay, that is called a counterexample. So therefore, we can say that the argument is invalid because if the argument was valid, we would never be able to find this false case. We would never be able to find this counterexample, much like what we saw before with modus ponens. So just as a review, if ever I ask you, is this expression or is this argument valid or invalid? The first thing I think we should do is try to find a counterexample. If we can find a counterexample, we're done and it's invalid. Okay, again, if we find a counterexample, we're done and and we can just say it's invalid. If we cannot find a counterexample, if there's a contradiction somewhere, then we can say this is valid. And at that point, what I probably will ask you to do is use the laws in order to prove it. Okay, use the laws in order to prove that it's valid. Okay, so those are types of questions that you might see on an exam or something like that. All right. So I'm going to stop the video here and I'm going to move on to the next video where we're going to do a little bit more on proofs.